What if I told you that the universe holds secrets so profound they could rewrite everything we know about existence? Picture this, a telescope so powerful it can peer back in time to witness the birth of the very first stars, or capture the faint glow of a distant exoplanet's atmosphere, searching for signs of life. This isn't science fiction, it's the future of space-based telescopes, and it's closer than you think. In this video, we're diving into 30 groundbreaking predictions about the future of space-based telescopes and the discoveries they'll unlock. From ultra-high-resolution imaging that will let us see distant worlds in stunning detail, to telescopes that can detect the faint ripples of gravitational waves from the edges of the cosmos, the possibilities are as vast as the universe itself. Imagine a world where we can map the invisible threads of dark matter or witness the explosive death of a star in real time. What if we could find definitive proof of extraterrestrial life or unravel the mysteries of the universe's earliest moments? These are just a few of the awe-inspiring advancements we'll explore. So, if you've ever gazed up at the night sky and wondered what lies beyond, stay with us. By the end of this video, you'll not only have a glimpse into the future of space exploration, but also a deeper understanding of how these incredible technologies will shape our understanding of the cosmos. The universe is calling, let's answer it together. Now, let's zoom in on the first of these incredible predictions, ultra-high-resolution imaging. Imagine being able to see a distant exoplanet not as a blurry dot, but in breathtaking detail, its continents, oceans, and even weather patterns visible from light years away. This isn't just a dream, it's the future of space-based telescopes, and it's all thanks to groundbreaking technologies like advanced adaptive optics and interferometry. Adaptive optics, for instance, will allow telescopes to correct distortions caused by Earth's atmosphere or other cosmic interference, delivering crystal-clear images. But the real game-changer is interferometry, where multiple telescopes work together as one giant instrument. By combining their data, these telescopes will achieve resolutions so sharp, they'll reveal details on distant worlds that were once thought impossible to see. Think about it, we could observe the surface of an exoplanet and analyze its geography, or even spot signs of potential habitability. This level of detail will revolutionize our understanding of distant solar systems and bring us closer than ever to answering the age-old question, are we alone in the universe? As we move forward, these advancements won't just expand our knowledge, they'll redefine what's possible in space exploration, and this is just the beginning. Next, we'll explore how future telescopes will observe the universe across multiple wavelengths, painting a fuller picture of the cosmos than ever before. Now, let's shift our gaze to the next groundbreaking prediction, multi-wavelength observatories. Picture this: instead of seeing the universe through just one lens, future telescopes will capture it across the entire electromagnetic spectrum, from radio waves to gamma rays. This means we'll no longer be limited to a narrow slice of what's out there. Instead, we'll have a panoramic view of the cosmos, revealing secrets that were once hidden in plain sight. Take radio waves, for example. They allow us to peer through cosmic dust and gas, uncovering the birthplaces of stars and galaxies. On the other end of the spectrum, gamma rays give us a front-row seat to the most energetic events in the universe, like supernova and black hole jets. By combining observations from these different wavelengths, we'll gain a richer, more complete understanding of how the universe works. Imagine being able to study a single galaxy in multiple wavelengths. In visible light, we might see its stars and structure. In infrared, we could detect heat from forming planets or hidden star nurseries. And in X-rays, we might spot the intense radiation from a supermassive black hole at its center. Together, these observations create a detailed portrait of the galaxy's life story, its past, present, and future. This multi-wavelength approach isn't just about seeing more, it's about understanding more. It will help us piece together the puzzle of cosmic phenomena, from the behavior of black holes to the origins of the universe itself. And as we continue to push the boundaries of what's possible, these observatories will open new doors to discovery, revealing the universe in ways we've never imagined. But the journey doesn't stop here. Next, we'll dive into how future telescopes will stream data to Earth in real time, bringing the wonders of the cosmos directly to our screens as they unfold. Now, let's step into the future of how we experience the cosmos, real-time data streaming. Imagine a world where the discoveries made by space telescopes aren't delayed by hours, days, or even weeks. Instead, they're beamed directly to Earth as they happen, allowing scientists and the public alike to witness the universe's most dramatic moments unfold in real time. This isn't just about faster data delivery, it's about transforming how we engage with space exploration. Picture this: a telescope detects a supernova explosion billions of light years away, and within seconds, that data is processed and shared with researchers around the globe. At the same time, enthusiasts and students tuning in from their homes can watch the event live, feeling as though they're right there in the control room. But how is this possible? The answer lies in cutting-edge technology and the power of artificial intelligence. Future telescopes will be equipped with advanced communication systems capable of transmitting vast amounts of data at unprecedented speeds. And here's where AI steps in. These intelligent systems will sift through the incoming data, identifying key events and anomalies in real time. This means scientists won't have to wait to analyze the information. They'll be alerted instantly to anything unusual or groundbreaking. For example, if a telescope spots a gamma-ray burst, AI can flag it immediately, allowing astronomers to focus their attention on studying the event while it's still happening. This real-time processing also opens the door to collaborative discoveries, as researchers from different fields can quickly share insights and work together to interpret the data. But the impact goes beyond science. Real-time streaming will make space exploration more accessible and engaging for everyone. Imagine live broadcasts of planetary flybys, asteroid collisions, or even the first signs of life on a distant exoplanet. These moments won't just belong to scientists, they'll belong to all of humanity, sparking curiosity and wonder in people of all ages. As we look ahead, the combination of real-time data streaming and AI promises to revolutionize our understanding of the universe. It's not just about seeing farther, it's about seeing faster, smarter, and together. And with that, we're ready to explore the next frontier: space-based gravitational wave detectors, where the universe's most elusive signals await. Now, let's turn our attention to one of the most exciting frontiers in space exploration: space-based gravitational wave detectors. These advanced instruments will allow us to listen to the universe in a way we've never been able to before, capturing the faint ripples in space-time caused by some of the most powerful events in the cosmos. Gravitational waves are like cosmic echoes, created when massive objects like black holes or neutron stars collide. On Earth, we've already detected these waves using facilities like LIGO and Virgo, but space-based detectors will take this science to a whole new level. By placing these detectors in space, we can avoid the noise and interference of Earth's environment, allowing us to pick up even fainter signals from much farther away. Imagine a network of satellites, each equipped with ultra-sensitive instruments, working together to detect gravitational waves. These detectors will be able to observe events that are billions of light years away, giving us a front-row seat to the collisions of supermassive black holes or the explosive mergers of neutron stars. These observations will not only help us understand the nature of these extreme objects, but also shed light on the early universe, revealing how galaxies and cosmic structures formed. One of the most exciting possibilities is the ability to detect gravitational waves from the very first moments after the Big Bang. These primordial ripples could provide clues about the universe's origins and the mysterious forces that shaped it. Space-based detectors will also allow us to study the properties of black holes and neutron stars in unprecedented detail, helping us answer questions about their formation, evolution, and behavior. But the benefits don't stop there. By combining gravitational wave data with observations from traditional telescopes, we'll gain a more complete picture of cosmic events. For example, if a telescope spots a gamma ray burst at the same time a gravitational wave detector picks up a signal, we'll know exactly what caused it, whether it was a black hole merger, a neutron-star collision, or something entirely new. This new era of gravitational wave astronomy will transform our understanding of the universe, revealing secrets that have been hidden for billions of years. It's not just about seeing the cosmos, it's about hearing it too. And with that, we're ready to dive into the next prediction, exoplanet atmosphere analysis, where we'll explore how future telescopes will search for signs of life beyond our solar system. Now, let's shift our gaze to the skies beyond our solar system, where the search for life takes center stage. Exoplanet atmosphere analysis is one of the most thrilling areas of space exploration, and future space telescopes are set to revolutionize this field. Imagine being able to study the air on distant worlds, searching for the chemical fingerprints of life, or even habitable conditions that could support it. This is where advanced spectrometers come into play, acting as cosmic detectives that can analyze the light passing through an exoplanet's atmosphere. These spectrometers will break down the light into its component colors, revealing the unique signatures of gases like oxygen, methane, carbon dioxide, and water vapor. Each of these gases tells a story. For example, oxygen could hint at the presence of photosynthetic life, while methane might suggest biological activity or geological processes. By studying these atmospheric compositions, scientists can determine whether a planet has the right ingredients to support life as we know it, or even life as we don't yet understand it. One of the most exciting prospects is the ability to detect biosignatures, chemical markers that could indicate the presence of life. Future telescopes will be so sensitive that they could spot these signatures on planets hundreds of light years away. Imagine the implications. We might one day find a world with an atmosphere rich in oxygen and methane, a combination that, on Earth, is almost always linked to living organisms. Such a discovery would be a game-changer, offering the first concrete evidence that we're not alone in the universe, but it's not just about finding life. These telescopes will also help us identify potentially habitable worlds. By analyzing the atmospheres of exoplanets, we can determine whether they have the right conditions for liquid water, a key ingredient for life as we know it. Some planets might have thick, toxic atmospheres, while others could have thin, breathable air. The data gathered will help us prioritize which worlds to study further, bringing us closer to answering one of humanity's oldest questions: are we alone? This new era of exoplanet exploration will also shed light on the diversity of planetary systems. We've already discovered thousands of exoplanets, from scorching hot gas giants to rocky worlds orbiting distant stars. But with advanced spectrometers, we'll be able to understand not just what these planets look like, but what they're made of and whether they could support life. It's like moving from black and white photos to full-color, high-definition images of the cosmos. As we continue to push the boundaries of what's possible, the next frontier awaits. Up next, we'll explore how future telescopes will map the invisible dark matter and uncover one of the universe's greatest mysteries. Stay tuned. Now, let's turn our attention to one of the most elusive and mysterious components of the universe: dark matter. While we can't see it directly, its presence is felt through its gravitational effects on galaxies and cosmic structures. Future space telescopes are poised to map the distribution of dark matter across the cosmos, offering us a clearer picture of this invisible force that shapes the universe. Dark matter makes up about 85% of all matter in the universe, yet it doesn't emit, absorb, or reflect light, making it incredibly difficult to detect. However, its gravitational influence is undeniable. It bends the light from distant galaxies, a phenomenon known as gravitational lensing. By studying these distortions, future telescopes will create detailed maps of dark matter, revealing where it clumps together and how it forms the cosmic web that connects galaxies. These maps will not only help us understand the structure of the universe, but also provide clues about the nature of dark matter itself. Is it made up of exotic particles we haven't yet discovered, or does it represent a new kind of physics altogether? By analyzing the distribution and behavior of dark matter, scientists hope to answer these questions and unlock one of the greatest mysteries in astrophysics. One of the most exciting aspects of this research is its potential to reshape our understanding of the cosmos. Dark matter plays a crucial role in the formation and evolution of galaxies, acting as the scaffolding upon which visible matter builds. Without it, galaxies as we know them wouldn't exist. By mapping its distribution, we'll gain insights into how galaxies form, grow, and interact over billions of years. Future telescopes will also use dark matter maps to test our current theories about the universe. For example, they could help us refine our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. By comparing observations with theoretical models, scientists can determine whether our current understanding of physics holds up, or if we need to rethink the fundamental laws that govern the cosmos. As we peer deeper into the universe, the invisible becomes visible and the unknown begins to take shape. Dark matter mapping is more than just a scientific endeavor. It's a journey into the heart of the universe's greatest mysteries. And with each new discovery, we move closer to understanding the true nature of the cosmos. Next, we'll dive into the dynamic world of time-domain astronomy, where telescopes will capture the universe in motion, revealing fleeting cosmic events as they unfold. Stay with us as we explore the next frontier of space-based discoveries. Now, let's shift our gaze to the ever-changing cosmos, where the universe reveals its most dramatic and fleeting moments. Time-domain astronomy is all about capturing the dynamic nature of the universe, and future space telescopes will take this to a whole new level. Imagine being able to watch the sky in real time, witnessing cosmic events as they happen: supernova exploding, gamma-ray bursts lighting up the darkness, and even asteroid collisions reshaping the surfaces of distant worlds. This is the promise of time-domain astronomy, and it's set to revolutionize how we observe and understand the universe. Unlike traditional astronomy, which often focuses on static images of the cosmos, time-domain astronomy is about motion and change. Future telescopes will monitor vast regions of the sky continuously, scanning for sudden bursts of light or other transient phenomena. These events are often unpredictable and short-lived, but they hold the key to understanding some of the most energetic and mysterious processes in the universe. For example, a supernova, the explosive death of a massive star, can outshine an entire galaxy for a brief moment, providing a wealth of information about stellar evolution and the creation of heavy elements. Gamma-ray bursts, on the other hand, are among the most powerful explosions in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. These bursts are thought to occur during the formation of black holes or the collision of neutron stars, and they offer a unique window into the extreme physics of these events. By capturing gamma-ray bursts in real time, future telescopes will allow scientists to study their origins and effects in unprecedented detail. But it's not just about the big, dramatic events. Time-domain astronomy will also shed light on smaller, yet equally fascinating phenomena. For instance, asteroid collisions in our solar system can provide clues about the formation and evolution of planetary systems. By observing these impacts as they happen, we can learn more about the composition and structure of asteroids, as well as the processes that shape the surfaces of planets and moons. One of the most exciting aspects of this field is its potential for discovery. Because transient events are often unpredictable, every observation has the potential to reveal something entirely new. Future telescopes will be equipped with advanced sensors and artificial intelligence systems that can quickly identify and analyze these events, ensuring that nothing is missed. This real-time data will not only enhance our understanding of the universe, but also allow scientists to respond rapidly to new discoveries, coordinating follow-up observations with ground-based telescopes and other instruments. As we move into this new era of time-domain astronomy, we'll be able to see the universe in a way we never have before, not as a static collection of objects, but as a dynamic, ever-changing tapestry of events. From the birth and death of stars to the collisions of asteroids and the formation of black holes, the cosmos will come alive before our eyes, and with each new observation, we'll gain a deeper appreciation for the incredible forces that shape our universe. Next, we'll explore how future telescopes will study interstellar objects, offering us a glimpse into the mysteries of planetary systems beyond our own. Stay tuned as we continue our journey through the future of space-based discoveries. Now, let's turn our attention to the mysterious visitors from beyond our solar system interstellar objects. These cosmic wanderers, like the famous Oumuamua, offer us a rare opportunity to study materials and processes from other star systems. Future space telescopes will be uniquely equipped to observe and analyze these objects, unlocking secrets about planetary systems far beyond our own. Interstellar objects are essentially messengers from distant corners of the galaxy. Unlike comets or asteroids that originate within our solar system, these objects travel through interstellar space, occasionally passing through our cosmic neighborhood. Oumuamua, the first confirmed interstellar object detected in 2017, sparked immense curiosity due to its unusual shape and behavior. Future telescopes will allow us to study such objects in much greater detail, providing insights into their composition, structure, and origins. One of the key challenges in studying interstellar objects is their speed and fleeting presence. They often pass through our solar system quickly, leaving little time for observation. However, next-generation telescopes will be designed to detect and track these objects more effectively. With advanced sensors and rapid response capabilities, these telescopes will capture detailed images and spectra, revealing the chemical makeup and physical properties of interstellar visitors. This data will help scientists determine whether these objects are rocky, icy, or even fragments of shattered planets. Moreover, studying interstellar objects can shed light on the diversity of planetary systems across the galaxy. By analyzing their composition, we can infer the types of materials present in other star systems and how they might differ from those in our own solar system. For example, if an interstellar object contains minerals or compounds not commonly found here, it could suggest unique planetary formation processes in its home system. This information could reshape our understanding of how planets and other celestial bodies form and evolve. Another exciting possibility is the detection of interstellar objects that may carry organic molecules or even potential signs of past life. While this remains speculative, the idea that such objects could transport materials or even microbial life between star systems is a fascinating area of research. Future telescopes equipped with high-resolution spectrometers will be able to search for these biosignatures, offering clues about the potential for life elsewhere in the universe. The study of interstellar objects also has practical implications for planetary defense. By understanding the trajectories and properties of these objects, we can better predict their paths and assess any potential risks they might pose to Earth. This knowledge will be invaluable as we continue to explore and protect our planet from cosmic hazards. As we look to the future, the ability to observe and analyze interstellar objects will open up a new frontier in astronomy. These enigmatic travelers hold the key to understanding not only our own solar system but also the broader galaxy. With each new discovery, we'll gain a deeper appreciation for the interconnectedness of the cosmos and the incredible diversity of worlds that exist beyond our own. Next, we'll dive into the revolutionary potential of quantum-enhanced telescopes, exploring how cutting-edge technology will redefine our ability to observe the universe. Stay with us as we continue to uncover the future of space-based discoveries. Now, let's shift our gaze to the cutting-edge realm of quantum-enhanced telescopes, where the marriage of quantum mechanics and astronomy promises to redefine how we explore the cosmos. Imagine a telescope that doesn't just observe the universe but does so with unprecedented speed and precision, thanks to the power of quantum technologies. This isn't science fiction, it's the future of space-based observation. Quantum-enhanced telescopes will leverage the principles of quantum mechanics to overcome some of the biggest challenges in astronomy today. One of the most exciting applications is quantum computing, which could revolutionize how we process the vast amounts of data collected by telescopes. Traditional computers struggle with the sheer volume and complexity of astronomical data, but quantum computers, with their ability to perform multiple calculations simultaneously, could analyze this information in a fraction of the time. This means faster discoveries and more efficient use of telescope resources. But the benefits don't stop there. Quantum sensors, another key component of these advanced telescopes, will enable measurements with extraordinary precision. For example, quantum entanglement, a phenomenon where particles become interconnected, no matter the distance between them, could be used to create ultra-sensitive detectors. These detectors will be capable of measuring faint signals from distant stars, galaxies, and even gravitational waves with incredible accuracy. This level of precision could help us uncover subtle details about the universe that were previously beyond our reach. Another groundbreaking application is quantum imaging. By harnessing the unique properties of quantum light, telescopes could capture images with higher resolution and less noise than ever before. This would allow us to see finer details in distant objects, such as the surfaces of exoplanets or the intricate structures of galaxies. Quantum imaging could also reduce the impact of atmospheric interference, making ground-based telescopes more effective and complementing space-based observatories. The integration of quantum technologies into telescopes also opens the door to entirely new ways of observing the universe. For instance, quantum communication could enable real-time data sharing between telescopes across vast distances, creating a global network of observatories working in perfect harmony. This collaborative approach would enhance our ability to monitor transient events like supernova or gamma-ray bursts as they happen. As we look ahead, the potential of quantum-enhanced telescopes is nothing short of transformative. These advancements will not only accelerate our understanding of the cosmos, but also push the boundaries of what's possible in astronomy. By combining the power of quantum mechanics with the ingenuity of space exploration, we're on the brink of a new era of discovery, one that will reveal the universe in ways we've only begun to imagine. Next, we'll explore how arrays of space telescopes working together as interferometers will achieve unprecedented resolution and sensitivity, taking our cosmic observations to the next level. Stay tuned as we continue to unveil the future of space-based telescopes. Now, let's turn our attention to the fascinating world of space-based interferometers, where multiple telescopes join forces to create a cosmic super-eye. Picture this: instead of relying on a single telescope, imagine a network of telescopes spread across space, working together as one. This collaborative approach, known as interferometry, will allow us to achieve levels of resolution and sensitivity that were once thought impossible. At its core, interferometry is about combining the light collected by multiple telescopes to create a single, highly detailed image. When these telescopes are positioned far apart, they act like a much larger telescope, effectively increasing their ability to resolve fine details. This technique has already been used on Earth with great success, but taking it into space opens up a whole new realm of possibilities. In space, there's no atmosphere to distort the light, and the distances between telescopes can be much greater, leading to even sharper images. One of the most exciting applications of space-based interferometers is their ability to study distant stars and exoplanets in extraordinary detail. For example, they could allow us to directly image the surfaces of stars, revealing features like sunspots and stellar flares with incredible clarity. They could also help us study the atmospheres of exoplanets, searching for signs of habitability or even life. By combining the data from multiple telescopes, we can detect faint signals that would otherwise be lost in the noise, giving us a clearer picture of these distant worlds. Another groundbreaking use of interferometers is in the study of black holes. By linking telescopes across vast distances, we can observe the intricate details of black hole event horizons and the swirling disks of matter that surround them. This could provide new insights into how black holes form, grow, and interact with their surroundings. It could also help us test some of the most fundamental predictions of Einstein's theory of general relativity. Space-based interferometers will also play a crucial role in studying gravitational waves. These ripples in space-time, caused by massive cosmic events like black hole mergers, are incredibly faint and difficult to detect. By using interferometers in space, we can increase the sensitivity of our detectors and observe gravitational waves from even more distant sources. This could open up a new window into the universe, allowing us to study events that are invisible to traditional telescopes. The potential of space-based interferometers doesn't stop there. They could also help us map the large-scale structure of the universe, revealing the distribution of galaxies and dark matter in unprecedented detail. This could shed light on some of the biggest mysteries in cosmology, such as the nature of dark energy and the ultimate fate of the universe. As we look to the future, the development of space-based interferometers represents a giant leap forward in our ability to explore the cosmos. By combining the power of multiple telescopes, we can achieve levels of precision and sensitivity that were once unimaginable. This collaborative approach will not only deepen our understanding of the universe, but also inspire new questions and discoveries that will shape the future of astronomy. Next, we'll dive into how artificial intelligence will analyze vast amounts of telescope data, uncovering hidden patterns and making groundbreaking discoveries. Stay with us as we continue to explore the incredible future of space-based telescopes. Now, let's shift our focus to the transformative role of artificial intelligence in the future of space-based telescopes. Imagine a world where the sheer volume of data collected by these powerful instruments is no longer a challenge but an opportunity. Artificial intelligence, or AI, is set to revolutionize how we process and interpret this data, unlocking discoveries that would otherwise remain hidden. At the heart of this revolution is the ability of AI to sift through massive datasets with incredible speed and precision. Space telescopes generate an overwhelming amount of information, from images of distant galaxies to spectra of exoplanet atmospheres. Traditional methods of analysis simply can't keep up with this deluge of data. That's where AI steps in. By using advanced algorithms, AI can identify patterns, anomalies, and trends that human researchers might miss. This capability will allow us to make sense of the cosmos in ways we never thought possible. One of the most exciting applications of AI in astronomy is its ability to detect exoplanets. By analyzing the subtle dips in a star's brightness caused by a passing planet, AI can identify potential candidates far more efficiently than manual methods. This not only speeds up the discovery process, but also increases the likelihood of finding Earth-like worlds in the habitable zones of their stars. AI can also help us study the atmospheres of these exoplanets, searching for chemical signatures that might indicate the presence of life. But AI's contributions don't stop at exoplanet hunting. It will also play a crucial role in understanding the large-scale structure of the universe. By analyzing data from galaxy surveys, AI can map the distribution of matter across vast cosmic distances, shedding light on the mysterious forces of dark matter and dark energy. This could help us answer some of the most profound questions in cosmology, such as why the universe is expanding at an accelerating rate. Another groundbreaking use of AI is in the study of transient events like supernova and gamma-ray bursts. These fleeting phenomena are often difficult to catch and analyze in real time. AI can monitor telescope data continuously, alerting astronomers to these events as they happen. This real-time analysis will allow us to study these cosmic explosions in unprecedented detail, providing new insights into the life cycles of stars and the origins of heavy elements. AI will also enhance our ability to classify and catalog celestial objects. From identifying different types of galaxies to distinguishing between various kinds of stellar explosions, AI can automate and refine these processes, freeing up astronomers to focus on interpreting the results. This will not only accelerate the pace of discovery, but also improve the accuracy of our cosmic inventories. Perhaps one of the most intriguing possibilities is AI's potential to uncover entirely new phenomena. By analyzing data in ways that go beyond human intuition, AI might detect signals or patterns that point to previously unknown cosmic events or objects. This could lead to the discovery of new types of stars, exotic forms of matter, or even evidence of advanced extraterrestrial civilizations. As we look to the future, the integration of artificial intelligence into space-based telescopes represents a paradigm shift in how we explore the universe. By harnessing the power of AI, we can turn the challenge of big data into an opportunity for groundbreaking discoveries. This partnership between human ingenuity and machine intelligence will not only deepen our understanding of the cosmos, but also inspire new questions that push the boundaries of science. Next, we'll explore how swarms of small, coordinated telescopes will work together to observe large areas of the sky simultaneously, opening up new possibilities for discovery. Stay tuned as we continue our journey into the future of space-based telescopes. Now, let's turn our attention to an exciting development in the world of space-based telescopes, the concept of swarms. Picture this: not just one powerful telescope, but dozens or even hundreds of smaller ones working together in perfect harmony. This is the future of space observation, where swarms of coordinated telescopes will revolutionize how we explore the cosmos. The idea behind telescope swarms is both simple and brilliant. Instead of relying on a single, massive instrument, these swarms consist of multiple smaller telescopes that operate as a unified system. Each telescope in the swarm is designed to observe a specific portion of the sky, and together they can cover vast areas simultaneously. This approach allows us to monitor the entire sky in ways that were previously impossible with traditional telescopes. One of the key advantages of telescope swarms is their ability to capture transient events in real time. Imagine a supernova exploding in a distant galaxy or a gamma-ray burst lighting up the cosmos. These events happen quickly and are often missed by single telescopes focused on a narrow field of view. But with a swarm, multiple telescopes can be directed to different parts of the sky, ensuring that no cosmic event goes unnoticed. This real-time monitoring will give astronomers unprecedented opportunities to study these fleeting phenomena as they unfold. Another benefit of telescope swarms is their versatility. Because they consist of many smaller units, they can be reconfigured to focus on specific targets or regions of interest. For example, if scientists want to study a particular star system or galaxy cluster, the swarm can be adjusted to concentrate its collective power on that area. This flexibility makes telescope swarms an incredibly powerful tool for both broad surveys and detailed observations. The coordination of these swarms relies on advanced technology, including artificial intelligence and sophisticated communication systems. Each telescope in the swarm must be able to share data with the others, creating a seamless network of observations. artificial intelligence plays a crucial role in managing this data flow, ensuring that the telescopes work together efficiently and that the information they collect is processed and analyzed in real time. Telescope swarms also have the potential to enhance our understanding of the universe's large-scale structure. By observing vast areas of the sky simultaneously, these swarms can map the distribution of galaxies, dark matter, and cosmic phenomena on an unprecedented scale. This could provide new insights into the forces shaping the universe, from the behavior of dark energy to the formation of galaxy clusters. But perhaps one of the most exciting possibilities is the ability of telescope swarms to search for signs of extraterrestrial life. By covering large areas of the sky, these swarms can scan for technosignatures, indicators of advanced civilizations, such as artificial structures or unusual energy emissions. This coordinated effort could bring us closer to answering one of humanity's most profound questions. Are we alone in the universe? As we look to the future, telescope swarms represent a bold new approach to space exploration. By combining the power of multiple instruments, they offer a level of coverage and flexibility that single telescopes simply cannot match. This innovative technology will open up new frontiers in astronomy, allowing us to explore the cosmos in ways we've only dreamed of. Next, we'll dive into how future telescopes will directly image black holes with greater clarity, revealing their structure and behavior in stunning detail. Stay with us as we continue to uncover the incredible possibilities of space-based telescopes. Now, let's shift our gaze to one of the most mysterious and captivating objects in the universe, black holes. While we've already captured groundbreaking images of these cosmic giants, the future of space-based telescopes promises to bring us even closer to understanding their secrets. Direct imaging of black holes is set to reach new heights, offering unprecedented clarity and detail that will transform our knowledge of these enigmatic phenomena. The first image of a black hole, captured in 2019 by the Event Horizon Telescope, was a monumental achievement. It revealed the shadow of a supermassive black hole at the center of the galaxy Messier 87, surrounded by a glowing ring of hot gas. But this was just the beginning. Future telescopes will build on this success, using advanced technologies to produce even sharper and more detailed images. These next-generation instruments will allow us to see black holes with a level of precision that was once thought impossible. One of the key advancements driving this progress is the development of larger and more sensitive space-based telescopes. By placing these instruments in orbit, we can avoid the distortions caused by Earth's atmosphere, resulting in clearer and more accurate images. Additionally, future telescopes will utilize longer baselines, meaning they will observe black holes from greater distances apart. This technique, known as interferometry, effectively creates a virtual telescope with a diameter as large as the distance between the individual instruments. The result, images with resolution so high that we can discern fine details in the structure and behavior of black holes. But it's not just about sharper images. Future telescopes will also capture black holes in different wavelengths of light, from radio waves to X-rays. This multi-wavelength approach will provide a more complete picture of how black holes interact with their surroundings. For example, we'll be able to observe the intense magnetic fields and swirling jets of particles that are ejected from the vicinity of black holes. These observations will help us understand the complex processes that occur near the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. Another exciting possibility is the ability to study black holes over time. By capturing a series of images, astronomers can create time-lapse sequences that reveal how black holes evolve and interact with their environments. This could include watching as black holes consume matter, triggering bursts of energy, or even observing the collision of two black holes. Such dynamic observations will provide invaluable insights into the life cycles of these cosmic objects and the role they play in shaping galaxies. Direct imaging of black holes will also shed light on some of the most profound questions in physics. For instance, by studying the properties of black holes, scientists can test the predictions of Einstein's theory of general relativity under extreme conditions. Any deviations from these predictions could point to new physics, potentially revolutionizing our understanding of gravity and the fundamental laws of the universe. As we look ahead, the ability to directly image black holes with greater clarity represents a giant leap forward in our quest to unravel the mysteries of the cosmos. These future observations will not only deepen our understanding of black holes, but also open new windows into the nature of space, time, and the universe itself. Next, we'll explore how space telescopes will peer back in time to observe the first stars and galaxies, illuminating the universe's early history. Stay tuned as we continue our journey through the incredible possibilities of space-based telescopes. Now let's journey even further back in time to an era when the universe was in its infancy. Imagine a time before galaxies, before stars, even before light itself could travel freely through space. This is the cosmic dawn, the period when the first stars and galaxies began to form, and future space telescopes are poised to give us an unprecedented view of this pivotal chapter in the universe's history. The cosmic dawn marks the end of the so-called Dark Ages, a time when the universe was filled with a dense fog of neutral hydrogen gas. As the first stars ignited, their intense ultraviolet light began to ionize this gas, gradually clearing the fog and allowing light to travel freely. This process, known as reionization, fundamentally transformed the universe, setting the stage for the formation of galaxies and the cosmic structures we see today. But until now, this era has remained largely hidden from our view, shrouded in the mists of time. Future space telescopes equipped with cutting-edge technology will change that. These instruments will be designed to detect the faintest traces of light from the earliest stars and galaxies, light that has traveled across billions of light years to reach us. By observing this ancient light, astronomers will be able to piece together the story of how the universe transitioned from a dark, featureless expanse to the vibrant, star-filled cosmos we know today. One of the key challenges in observing the cosmic dawn is the extreme distance and faintness of these early objects. To overcome this, future telescopes will be equipped with highly sensitive detectors capable of capturing even the dimmest signals. They will also operate in specific wavelengths of light, such as infrared, which is less affected by the expansion of the universe and can reveal the faint glow of the first stars and galaxies. But it's not just about seeing these objects, it's about understanding them. By studying the light from the cosmic dawn, scientists will be able to determine the properties of the first stars and galaxies, such as their size, temperature, and composition. This information will provide crucial insights into how these early structures formed and evolved, shedding light on the processes that shaped the universe as we know it. Another exciting possibility is the detection of the very first supernova, the explosive deaths of the earliest stars. These cataclysmic events would have seeded the universe with heavy elements, the building blocks of planets and life. By observing these ancient supernovae, astronomers can trace the origins of the elements that make up everything around us, from the iron in our blood to the silicon in our smartphones. The cosmic dawn also holds clues to one of the greatest mysteries in cosmology, the nature of dark matter. The first stars and galaxies formed in the gravitational wells created by dark matter, and their distribution and properties can reveal important information about this elusive substance. By mapping the cosmic dawn, future telescopes could help us understand the role dark matter played in shaping the early universe. As we peer back in time to the cosmic dawn, we're not just observing the past, we're uncovering the origins of everything. These observations will provide a window into the universe's formative years, revealing how the first stars and galaxies lit up the cosmos and set the stage for the rich tapestry of galaxies, stars, and planets we see today. Next, we'll turn our attention to how space telescopes will revolutionize our understanding of our own solar system, exploring planets, moons, and asteroids with unprecedented detail. Stay with us as we continue to explore the incredible future of space-based telescopes. Now, let's bring our focus closer to home and explore how future space telescopes will revolutionize our understanding of our own solar system. While we've marveled at distant galaxies and the cosmic dawn, there's still so much to uncover right in our celestial backyard. Planets, moons, and asteroids within our solar system hold secrets that could reshape our understanding of planetary formation, evolution, and even the potential for life beyond Earth. Future space telescopes will be equipped with advanced imaging and spectroscopic tools, allowing us to study these objects in unprecedented detail. Imagine being able to map the surface of distant moons like Europa or Enceladus with the same clarity we use to study Earth's continents. These icy worlds, believed to harbor subsurface oceans, could hold clues about the potential for life in our solar system. By analyzing their surfaces and plumes of water vapor, telescopes will help scientists determine the chemical composition of these hidden oceans and assess their habitability. Asteroids, often considered relics from the early solar system, will also come under the spotlight. These rocky bodies carry valuable information about the conditions present during the formation of our solar system over 4.5 billion years ago. Future telescopes will not only map their surfaces but also analyze their composition, revealing the building blocks that eventually formed planets like Earth. This knowledge could even pave the way for asteroid mining, as we identify resources that could support future space exploration and colonization. Planets like Mars, Venus, and the gas giants will also benefit from this new era of observation. For Mars, telescopes could monitor seasonal changes, weather patterns, and even potential signs of past or present microbial life. Venus, often called Earth's twin, will be scrutinized for clues about its runaway greenhouse effect and whether it once harbored oceans. Meanwhile, the gas giants Jupiter and Saturn will be studied in greater detail, with telescopes capturing high-resolution images of their swirling storms, intricate ring systems, and diverse moons. One of the most exciting prospects is the ability to observe transient events in real time. Imagine watching a volcanic eruption on Io, Jupiter's fiery moon, or witnessing a massive storm forming on Saturn. These dynamic processes, which were once fleeting and hard to capture, will be monitored continuously, providing scientists with a wealth of data to understand the inner workings of these worlds. But it's not just about observation, it's about discovery. Future telescopes could identify new moons, rings, or even previously unknown dwarf planets lurking in the outer reaches of our solar system. Each new discovery will add another piece to the puzzle, helping us understand how our solar system formed, evolved, and continues to change. As we turn our gaze inward, we're reminded that our solar system is a treasure trove of mysteries waiting to be unlocked. With the power of future space telescopes, we'll explore these worlds like never before, uncovering secrets that could redefine our place in the cosmos. Next, we'll venture into the realm of the extraordinary, exploring how future telescopes might detect signs of advanced extraterrestrial civilizations. Stay with us as we continue to uncover the incredible possibilities of space-based telescopes. Now, let's shift our gaze beyond our solar system and into the realm of the extraordinary. Imagine a future where space telescopes could detect signs of advanced extraterrestrial civilizations. This isn't science fiction, it's a real possibility that could redefine our understanding of life in the universe. Future telescopes equipped with cutting-edge technology might be able to identify megastructures built by intelligent beings far beyond our own world. One of the most intriguing concepts is the detection of Dyson spheres. These hypothetical structures, first proposed by physicist Freeman Dyson, are massive constructs designed to harness the energy of an entire star. If such a megastructure exists, it would block or alter the star's light in ways that future telescopes could detect. By analyzing the light patterns of distant stars, astronomers could search for anomalies that suggest the presence of these colossal energy harvesting systems. Imagine the implications of discovering a star partially obscured by a Dyson sphere. It would be one of the most profound discoveries in human history. But Dyson spheres are just the beginning. Future telescopes might also detect other types of megastructures, such as orbital rings, space habitats, or even artificial planets. These structures could emit unique signatures, such as unusual heat patterns or reflective surfaces, that stand out against the natural background of space. Advanced spectroscopic tools would allow scientists to analyze these signatures in detail, searching for evidence of materials or technologies that couldn't have formed naturally. The search for alien megastructures isn't just about finding physical objects, it's also about looking for technosignatures. These are signs of advanced technology, such as laser communications, industrial pollution in a planet's atmosphere, or even the waste heat from massive energy consumption. Future telescopes, with their unparalleled sensitivity and precision, could scan the skies for these subtle clues, bringing us closer to answering the age-old question, are we alone in the universe? This quest isn't just about discovery, it's about perspective. Finding evidence of an advanced civilization would challenge our understanding of intelligence, technology, and our place in the cosmos. It would remind us that the universe is vast, mysterious, and full of possibilities we've yet to imagine. As we continue to push the boundaries of what's possible with space telescopes, the search for alien megastructures represents one of the most exciting frontiers in astronomy. Next, we'll dive into how these telescopes will search for biosignatures on distant worlds, potentially confirming the existence of extraterrestrial life. Stay with us as we explore the next chapter in the future of space-based discoveries. Now, let's turn our attention to one of the most profound questions humanity has ever asked. Are we alone in the universe? Future space telescopes will play a pivotal role in answering this question by searching for biosignatures, chemical or physical indicators of life on distant worlds. This isn't just about finding water or oxygen. It's about identifying the complex combinations of gases, molecules, and other markers that could only be produced by living organisms. Imagine a telescope so advanced that it can analyze the atmosphere of an exoplanet light years away. By studying the light that passes through or reflects off a planet's atmosphere, scientists can detect the presence of gases like methane, ozone, or even phosphine, a gas that on Earth is often linked to biological activity. These telescopes will use spectroscopy, a technique that breaks down light into its component colors, to reveal the chemical fingerprints of distant atmospheres. If a planet shows signs of gases that shouldn't exist together without life, it could be a strong hint that we're not alone. But biosignatures aren't just about gases. Future telescopes might also look for surface features that suggest life, such as vegetation or microbial mats. For example, certain wavelengths of light could reveal the presence of chlorophyll, the pigment plants use for photosynthesis. Even more intriguing, telescopes might detect seasonal changes in a planet's surface color, hinting at the growth and decay of life forms over time. These observations would provide compelling evidence that life exists beyond Earth. Of course, detecting biosignatures isn't easy. Scientists will need to rule out non-biological explanations for the signals they observe. For instance, volcanic activity can produce methane, and certain chemical reactions can create oxygen without life being involved. That's why future telescopes will need to gather as much data as possible, combining atmospheric analysis with observations of a planet's surface, climate, and even its orbit around its star. Only by piecing together multiple lines of evidence can we confidently say we've found signs of life. The implications of discovering extraterrestrial life are staggering. It would not only answer one of humanity's oldest questions, but also reshape our understanding of biology, chemistry, and the conditions necessary for life to thrive. It would remind us that life, in all its forms, might be far more common in the universe than we ever imagined. As we continue to explore the cosmos, the search for biosignatures represents one of the most exciting and ambitious goals of space-based astronomy. Next, we'll delve into how telescopes will observe the ripples in space-time caused by massive cosmic events, opening a new window into the universe's most extreme phenomena. Stay tuned as we uncover the next frontier in space exploration. Now, let's shift our gaze to one of the most mind-bending phenomena in the universe, the ripples in space-time known as gravitational waves. These waves, first predicted by Albert Einstein over a century ago, are caused by some of the most violent and energetic events in the cosmos, colliding black holes, merging neutron stars, and even the birth of the universe itself. Future space telescopes will take our ability to detect and study these ripples to unprecedented levels, offering us a whole new way to explore the universe. Gravitational waves are like cosmic echoes created when massive objects accelerate or collide, sending ripples through the fabric of space-time. On Earth, observatories like LIGO and Virgo have already detected these waves, but space-based telescopes will take this science to the next level. By placing detectors in space far from the noise and vibrations of Earth, we'll be able to observe gravitational waves with far greater sensitivity and precision. This will allow us to detect events that are too faint or too distant for ground-based observatories to pick up. One of the most exciting prospects is the ability to observe the mergers of supermassive black holes. These colossal collisions, which can occur when galaxies merge, produce gravitational waves with frequencies that are too low for Earth-based detectors to catch. Space-based telescopes, however, will be perfectly tuned to detect these low-frequency waves, giving us a front-row seat to some of the most dramatic events in the universe. Imagine witnessing the moment two black holes, each billions of times more massive than our Sun, spiral together and merge, sending shockwaves through space-time itself. But it's not just black holes. Space-based gravitational wave detectors will also allow us to study the remnants of neutron star collisions, events that not only produce gravitational waves but also light, gamma rays, and even heavy elements like gold and platinum. By combining gravitational wave observations with traditional telescope data, we'll gain a more complete picture of these cataclysmic events, shedding light on the origins of the elements that make up our world. Perhaps most intriguingly, space-based telescopes could give us a glimpse into the very early universe. The Big Bang itself is thought to have produced a background of gravitational waves, often referred to as the cosmic gravitational wave background. Detecting these primordial ripples would provide direct evidence of the universe's birth and help us understand the conditions that existed in the first moments after the Big Bang. It's like listening to the echoes of creation itself. The ability to observe space-time ripples will revolutionize our understanding of the universe, revealing hidden details about the most extreme objects and events in existence. As we continue to refine this technology, we'll unlock new insights into the nature of gravity, the structure of space-time, and the history of the cosmos. Next, we'll explore how telescopes will monitor Earth's climate from space, providing critical data to help us understand and protect our planet. Stay with us as we uncover the next chapter in the story of space exploration. Now, let's turn our attention closer to home, where space-based telescopes will play a vital role in understanding and protecting our planet. While these instruments are often associated with exploring distant galaxies and cosmic phenomena, they are also incredibly powerful tools for monitoring Earth's climate. By observing our planet from space, telescopes will provide critical data that helps scientists track environmental changes, predict weather patterns, and address the challenges of climate change. Imagine having a bird's-eye view of Earth where every forest, ocean, and glacier is visible in stunning detail. Space-based telescopes equipped with advanced sensors will monitor key indicators of climate health, such as temperature changes, ice melt, deforestation, and ocean currents. This data is essential for understanding how our planet is responding to human activity and natural processes. For example, by tracking the shrinking of polar ice caps over time, scientists can better predict rising sea levels and their impact on coastal communities. One of the most significant advantages of space-based climate monitoring is the ability to observe the entire planet consistently. Unlike ground-based sensors, which are limited to specific locations, telescopes in space can provide a global perspective. This allows researchers to detect patterns and trends that might otherwise go unnoticed. For instance, satellites have already revealed the alarming rate at which rainforests are disappearing, providing evidence that has spurred international efforts to combat deforestation. But it's not just about observing changes. Space-based telescopes will also help us predict future climate events. By analyzing data on atmospheric conditions, ocean temperatures, and wind patterns, scientists can improve weather forecasting models. This means more accurate predictions of hurricanes, droughts, and other extreme weather events, giving communities more time to prepare and respond. In a world increasingly affected by climate change, this kind of information is invaluable. Moreover, space-based climate monitoring will play a crucial role in tracking greenhouse gas emissions. Telescopes equipped with specialized instruments can measure the concentration of carbon dioxide, methane, and other gases in the atmosphere. This data helps governments and organizations assess the effectiveness of policies aimed at reducing emissions and combating global warming. It's like having a global carbon footprint tracker in the sky. As we continue to face the challenges of a changing climate, space-based telescopes will be indispensable tools for understanding and protecting our planet. They offer a unique perspective that combines the vastness of space with the immediacy of Earth's environmental needs. Next, we'll delve into how telescopes will study ancient light to uncover the history of the universe, revealing secrets about the formation of galaxies and stars. Stay tuned as we journey deeper into the cosmos. Now, let's shift our gaze even further back in time, to a period when the universe was in its infancy. Space-based telescopes will act as cosmic archaeologists, studying ancient light to piece together the history of the universe. This light, which has traveled billions of years to reach us, carries secrets about the formation of galaxies, stars, and even the very fabric of space itself. By analyzing this ancient light, scientists can uncover the story of how the universe evolved from its earliest moments to the vast, complex cosmos we see today. One of the most fascinating aspects of this research is the ability to observe the universe as it was billions of years ago. Telescopes like the James Webb Space Telescope are designed to detect infrared light, which allows them to see through cosmic dust and observe the first galaxies that formed after the Big Bang. These galaxies, now incredibly distant and faint, hold clues about how the universe transitioned from a dark, empty void to a vibrant tapestry of stars and galaxies. It's like having a time machine that lets us witness the birth of the cosmos. But the study of ancient light goes beyond just observing distant galaxies. It also helps us understand the processes that shape the universe. For example, by analyzing the light from quasars, extremely bright objects powered by supermassive black holes, scientists can trace the distribution of matter in the early universe. This information reveals how galaxies and large-scale structures like galaxy clusters and filaments formed over time. It's a bit like piecing together a cosmic puzzle where each piece of light tells part of the story. Another exciting area of space-based archaeology is the study of the cosmic microwave background, or CMB. This faint glow left over from the Big Bang is essentially the oldest light in the universe. By mapping tiny variations in the CMB, telescopes can provide insights into the conditions of the early universe and how it expanded over time. These observations help refine our understanding of fundamental physics, including the nature of dark matter and dark energy, which make up the majority of the universe's content. Space-based telescopes will also shed light on the life cycles of stars. By observing ancient starlight, scientists can determine how the first stars formed, lived, and died, seeding the universe with the elements necessary for life. This process, known as stellar nucleosynthesis, is responsible for creating the carbon, oxygen, and other elements that make up planets, plants, and even us. In a way, studying ancient light is like tracing our own cosmic ancestry. As we continue to explore the universe's past, space-based telescopes will reveal even more about the origins of everything we see around us. From the first flickers of starlight to the formation of galaxies, these instruments will help us piece together the grand narrative of the cosmos. Next, we'll explore how telescopes will detect high-energy particles from cosmic events, offering new insights into the most extreme phenomena in the universe. Stay with us as we uncover more mysteries of the cosmos. Now, let's turn our attention to the invisible messengers of the cosmos, high-energy particles. Future space-based telescopes will not only observe light but also detect these particles, offering a new window into the most extreme events in the universe. Imagine being able to see the aftermath of a supernova or the collision of two black holes not just through light, but through the particles they send hurtling across space. These particles, often traveling at nearly the speed of light, carry information about the violent processes that created them, giving us a deeper understanding of the universe's most energetic phenomena. One of the key tools for this kind of research will be space-based particle detectors. Unlike traditional telescopes that focus on light, these detectors are designed to capture high-energy particles like cosmic rays, neutrinos, and gamma rays. Cosmic rays, for example, are charged particles that originate from supernova, black holes, and other high-energy sources. By studying these particles, scientists can learn about the conditions in these extreme environments, such as the intense magnetic fields and shock waves that accelerate particles to such incredible speeds. Neutrinos, often called ghost particles, are another fascinating focus. These nearly massless particles can travel through entire planets without interacting with matter, making them incredibly difficult to detect. However, space-based neutrino detectors will be able to capture these elusive particles, providing clues about the inner workings of supernova and the cores of active galaxies. Neutrinos are like cosmic fingerprints, carrying information about the processes that occur deep within these powerful objects. Gamma rays, the most energetic form of light, are also a critical part of this story. Space telescopes equipped with gamma-ray detectors will observe the bursts of energy released during events like black hole mergers or the collapse of massive stars. These gamma-ray bursts are some of the most powerful explosions in the universe, and studying them helps us understand the physics of extreme gravity and the behavior of matter under conditions we can't replicate on Earth. By combining observations of light with data from particle detectors, future telescopes will give us a more complete picture of cosmic events. For example, when a supernova occurs, we'll be able to see the light it emits, detect the neutrinos it produces, and measure the cosmic rays it sends out. This multi-messenger approach will revolutionize our understanding of the universe, allowing us to piece together the full story of these extraordinary events. As we continue to explore the cosmos, space-based particle detectors will open up new frontiers in our quest to understand the universe's most extreme phenomena. From the remnants of ancient supernova to the collisions of black holes, these detectors will reveal the hidden side of the cosmos, showing us that there's far more to the universe than meets the eye. Next, we'll dive into how telescopes will use pulsars and other cosmic phenomena to create ultra-precise space-based clocks, unlocking new possibilities for timekeeping and navigation. Stay tuned as we uncover more wonders of the universe. Now, let's shift our focus to the fascinating concept of timekeeping in space. Imagine a clock so precise that it could keep time with an accuracy measured in billionths of a second, not just here on Earth, but across the vast expanse of the cosmos. This is where space-based timekeeping comes into play, and it's set to revolutionize how we measure time in the universe. At the heart of this innovation are pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. These beams are so regular that pulsars act as natural clocks, ticking with incredible precision. Future space telescopes will harness the power of pulsars to create ultra-precise space-based clocks. By observing the timing of these pulses, scientists can develop a new standard for timekeeping that far surpasses anything we have today. But pulsars aren't the only cosmic phenomena that will play a role in this. Other celestial objects like quasars and even the faint echoes of gravitational waves could also contribute to this new era of timekeeping. Gravitational waves, for instance, ripple through space-time in predictable patterns, offering another way to measure time with extraordinary accuracy. By combining data from these sources, space telescopes will create a network of cosmic clocks that can synchronize time across the universe. This level of precision isn't just a scientific curiosity, it has real-world applications. For example, ultra-precise space-based clocks could improve navigation for spacecraft, allowing them to determine their position with unprecedented accuracy. It could also enhance our ability to detect subtle changes in the fabric of space-time, such as those caused by passing gravitational waves or the expansion of the universe. Even here on Earth, this technology could lead to more accurate global positioning systems and advancements in fields like telecommunications and quantum computing. The implications of space-based timekeeping go beyond practical applications. It could also deepen our understanding of the universe itself. By studying the timing of pulsars and other cosmic phenomena, scientists can test theories of gravity, explore the nature of dark energy, and even search for anomalies in the laws of physics. It's like having a universal metronome that keeps time for the entire cosmos, helping us uncover its deepest secrets. As we look to the future, space-based timekeeping represents a bold step forward in our quest to understand the universe. It's a reminder that even something as fundamental as time can be redefined by the wonders of space exploration. Next, we'll explore how telescopes will use gravitational lensing to magnify distant objects, revealing details about the early universe that were once beyond our reach. Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's turn our attention to one of the most fascinating tools in the cosmic toolbox: gravitational lensing. Picture this: a massive object like a galaxy or a cluster of galaxies warps the fabric of space-time around it. When light from a distant object passes through this warped space, it bends, much like how a magnifying glass bends light. This phenomenon, known as gravitational lensing, acts as a natural telescope, magnifying distant objects that would otherwise be too faint or small to see. Future space telescopes will harness this cosmic magnifying glass to peer deeper into the universe than ever before. By observing how light bends around massive objects, these telescopes will reveal details about galaxies, stars, and even exoplanets that formed billions of years ago. It's like having a front-row seat to the early universe, allowing us to witness the birth and evolution of cosmic structures. One of the most exciting applications of gravitational lensing is its ability to magnify the light from the first galaxies that formed after the Big Bang. These ancient galaxies are incredibly faint, but with the help of gravitational lensing, space telescopes will be able to study their shapes, sizes, and compositions in unprecedented detail. This could provide crucial insights into how the universe transitioned from a dark, empty void to the vibrant cosmos we see today. But gravitational lensing isn't just about looking back in time. It's also a powerful tool for studying dark matter. Since dark matter doesn't emit light, it's invisible to traditional telescopes. However, its presence can be detected through its gravitational effects on light. By analyzing how light bends around massive objects, scientists can map the distribution of dark matter in the universe, shedding light on one of its greatest mysteries. The potential of gravitational lensing doesn't stop there. It could also help us discover and study exoplanets in distant star systems. When a star passes in front of a more distant star, its gravity can act as a lens, magnifying the light from the background star. If the foreground star has planets, their gravity can create additional distortions in the light, revealing their presence and even providing clues about their atmospheres. As we continue to explore the universe, gravitational lensing will play a key role in uncovering its secrets. It's a reminder that even the most distant and elusive objects in the cosmos can be brought into focus with the right tools and techniques. Next, we'll dive into how space telescopes will enhance the search for extraterrestrial intelligence, scanning the skies for signs of advanced civilizations. Stay tuned as we venture further into the unknown. Now, shifting our gaze to the stars, let's explore how future space telescopes will revolutionize the search for extraterrestrial intelligence. For decades, scientists have been scanning the skies for signs of life beyond Earth. But with the next generation of space-based telescopes, this search is about to reach new heights. These advanced instruments will be equipped to detect technosignatures, indicators of advanced technology or civilizations that could reveal the presence of intelligent life in the universe. Imagine a telescope so sensitive it can pick up faint signals or patterns that might be produced by alien technology. These could range from artificial light sources on distant planets to unusual energy emissions that don't align with natural phenomena. Space-based telescopes free from the interference of Earth's atmosphere will have a clearer view of the cosmos, making them ideal for spotting these subtle clues. One of the most promising avenues is the search for megastructures like Dyson spheres, which hypothetical advanced civilizations might build to harness the energy of their stars. Future telescopes could detect the telltale dimming of a star as such a structure passes in front of it, or even identify the heat signatures of these massive constructs. Similarly, they might spot laser communications or other forms of directed energy that could serve as evidence of intelligent life. But the search for extraterrestrial intelligence isn't just about looking for big, obvious signs. It's also about analyzing the finer details. For example, future telescopes could examine the atmospheres of exoplanets for chemical imbalances that might indicate industrial activity. High levels of pollutants or artificial compounds could be a red flag that a civilization has reached a technological stage similar to our own. What makes this search even more exciting is the role of artificial intelligence. Advanced algorithms will sift through vast amounts of data collected by these telescopes, identifying patterns or anomalies that human researchers might miss. This collaboration between cutting-edge technology and human curiosity could bring us closer than ever to answering one of humanity's oldest questions: are we alone in the universe? As we continue to push the boundaries of what's possible, space-based telescopes will not only expand our understanding of the cosmos, but also bring us closer to discovering whether we share it with other intelligent beings. Next, we'll delve into how these telescopes will study cosmic rays, uncovering the origins and impact of these high-energy particles. Stay with us as we journey deeper into the mysteries of the universe. Now, let's turn our attention to the invisible messengers of the cosmos' cosmic rays. These high-energy particles, traveling at nearly the speed of light, have long puzzled scientists. Where do they come from? What can they tell us about the universe? Future space-based telescopes are set to unlock these mysteries, offering unprecedented insights into the origins and impact of cosmic rays. Cosmic rays are not rays in the traditional sense, but rather charged particles, such as protons and atomic nuclei, that zip through space. They originate from some of the most extreme environments in the universe: supernova explosions, black hole jets, and even the remnants of ancient stellar collisions. When these particles collide with Earth's atmosphere, they create cascades of secondary particles, but studying them from the ground has its limitations. Earth's atmosphere acts as a filter, distorting the data and making it harder to trace their true origins. This is where space-based telescopes come in. Positioned above the atmosphere, these instruments will have a clear, unobstructed view of cosmic rays as they travel through space. By detecting and analyzing these particles directly, scientists can piece together their journey across the cosmos. For instance, future telescopes might identify the specific regions of the sky where cosmic rays are most abundant, pointing us toward their sources. This could reveal new details about the violent processes that create them, such as the shock waves from supernova or the powerful magnetic fields around black holes. But cosmic rays are more than just cosmic curiosities. They play a crucial role in shaping the universe. These particles can influence the formation of stars and galaxies by heating interstellar gas and triggering chemical reactions. They also pose challenges for space exploration, as prolonged exposure to cosmic rays can damage spacecraft and harm astronauts. By studying them in detail, future telescopes will help us better understand these effects and develop strategies to mitigate them. One of the most exciting possibilities is the potential to uncover new physics. Some cosmic rays carry energies so high that they defy our current understanding of particle physics. Future telescopes might detect particles with energies beyond what our largest particle accelerators can produce, offering clues about the fundamental forces and particles that govern the universe. Could these observations lead to the discovery of new particles or even new dimensions? The possibilities are as vast as the cosmos itself. As we continue to explore the universe, space-based telescopes will shine a light on the invisible forces that shape it. By unraveling the secrets of cosmic rays, we'll gain a deeper understanding of the universe's most extreme environments and the fundamental laws that govern them. Next, we'll dive into how these telescopes will conduct a comprehensive census of exoplanets, identifying thousands of new worlds. Stay tuned as we uncover more about the future of space exploration. Now, let's shift our gaze to the stars and the countless worlds that orbit them. One of the most ambitious goals for future space-based telescopes is to conduct a comprehensive census of planets that exist beyond our solar system. Imagine a cosmic survey that doesn't just count these distant worlds but also maps their characteristics, bringing us closer to understanding the diversity of planetary systems across the galaxy. Today, we know of thousands of exoplanets thanks to missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS. But these are just the tip of the iceberg. Future telescopes will take this search to the next level, identifying tens of thousands of new worlds with unprecedented precision. These instruments will use advanced techniques like transit photometry, which detects the slight dimming of a star as a planet passes in front of it, and radial velocity, which measures the star's wobble caused by an orbiting planet's gravitational pull. What makes this census so groundbreaking is its scope. Future telescopes won't just focus on nearby stars, they'll scan vast regions of the galaxy, uncovering planets in a wide range of sizes, compositions, and orbits. From rocky super-Earths to gas giants, and even Earth-like worlds in the habitable zones of their stars, this census will paint a detailed picture of planetary diversity. It's like creating a galactic atlas where each new discovery adds another piece to the puzzle of how planets form and evolve. But the census won't stop at simply finding these worlds. Future telescopes will also analyze their atmospheres, searching for signs of water, oxygen, methane, and other molecules that could hint at habitability or even life. By studying the chemical fingerprints of these atmospheres, scientists can determine which planets might have the right conditions to support life as we know it. This opens the door to one of the most profound questions in science. Are we alone in the universe? The implications of this census go beyond science. It could reshape our understanding of our place in the cosmos. Discovering thousands of new worlds, some of which might resemble Earth, could inspire a new generation of explorers and dreamers. It could also guide future missions, helping us decide which planets to study in greater detail or even visit one day. As we look to the future, the space-based exoplanet census promises to be one of the most transformative endeavors in astronomy. It's not just about finding new worlds, it's about understanding the story of planets, stars, and the galaxy itself. Next, we'll explore how telescopes will track the life cycles of stars from their fiery births to their dramatic deaths. Stay with us as we continue our journey through the future of space-based discoveries. Now, let's turn our attention to the life stories of stars themselves, those celestial giants that light up the universe. Future space-based telescopes will revolutionize our understanding of stellar evolution, allowing us to witness the entire life cycle of stars, from their fiery beginnings to their dramatic final acts. This isn't just about observing stars, it's about piecing together the cosmic narrative of how they are born, live, and die. Stars begin their lives in vast clouds of gas and dust known as stellar nurseries. Future telescopes will peer into these cosmic cradles with incredible clarity, capturing the moment when gravity pulls these clouds together, igniting the nuclear fusion that powers a star. Imagine watching a star being born in real time, seeing the swirling chaos of gas and dust coalesce into a glowing sphere of light. These observations will help us understand the conditions needed for star formation and why some regions of space are more fertile than others. As stars mature, they enter the main sequence phase, where they spend the majority of their lives burning hydrogen into helium. Future telescopes will monitor these stars in unprecedented detail, tracking changes in their brightness, temperature, and composition. This will give us insights into how stars like our Sun evolve over billions of years, and how their energy output affects the planets orbiting them. We'll also learn more about the different types of stars, from small, dim red dwarfs to massive, luminous blue giants, and how their life cycles differ. But the most dramatic moments in a star's life come at the end. For smaller stars, this means a quiet fade into a white dwarf, surrounded by a glowing planetary nebula. For larger stars, it's a spectacular explosion known as a supernova, which can outshine an entire galaxy for a brief moment. Future telescopes will capture these events in stunning detail, revealing the processes that trigger these cosmic fireworks and the heavy elements they scatter into space elements that eventually form new stars, planets, and even life. One of the most exciting prospects is the ability to study the remnants of these stellar deaths. Telescopes will observe neutron stars and black holes, the dense cores left behind after a supernova, with incredible precision. These observations will help us understand the extreme physics at play in these objects, from the intense gravitational fields of black holes to the rapid spins of neutron stars. We might even witness the collision of two neutron stars, an event that ripples space-time and creates gold and other heavy elements. By tracking the life cycles of stars, future telescopes will not only deepen our understanding of these celestial objects, but also shed light on the broader processes that shape the universe. From the birth of stars to the creation of elements essential for life, stellar evolution is a story that connects us all to the cosmos. Next, we'll explore how telescopes will observe the formation and evolution of galaxies, uncovering the grand architecture of the universe. Stay tuned as we continue our journey through the future of space-based discoveries. Now, let's shift our gaze to the grand tapestry of the cosmos galaxies. These vast collections of stars, gas, and dust are the building blocks of the universe, and future space-based telescopes will allow us to witness their formation and evolution like never before. By studying galaxies, we'll uncover the secrets of how these colossal structures come together, grow, and change over billions of years, revealing the intricate architecture of the universe itself. Galaxies begin their lives in the early universe, emerging from the faint glow of the cosmic dawn. future telescopes will peer back in time, capturing the faint light of these infant galaxies as they form from the primordial soup of hydrogen and helium. Imagine seeing the first clumps of matter coalesce, slowly pulling together under gravity's influence to create the earliest galaxies. These observations will help us understand the conditions that allowed galaxies to form and why they take on such a variety of shapes, from spirals to ellipticals to irregular clusters. As galaxies mature, they grow through a combination of star formation and mergers with other galaxies. Future telescopes will track these processes in incredible detail, showing how galaxies accumulate gas to fuel new stars and how collisions between galaxies reshape their structures. We'll witness the birth of new stars within these galaxies, as well as the explosive deaths of older ones, which enrich the galaxy with heavy elements. These observations will give us a clearer picture of how galaxies evolve over time and how their environments influence their growth. One of the most fascinating aspects of galaxy formation is the role of dark matter. This mysterious substance, which makes up most of the universe's mass, acts as an invisible scaffold, guiding the formation and structure of galaxies. Future telescopes will map the distribution of dark matter around galaxies, revealing how it shapes their growth and movement. By studying the interplay between dark matter and visible matter, we'll gain new insights into the forces that govern the universe on the largest scales. Galaxies are also home to supermassive black holes, which lurk at their centers and play a crucial role in their evolution. Future telescopes will observe how these black holes grow and interact with their host galaxies, sometimes powering incredibly bright phenomena like quasars. We'll learn how black holes influence star formation, regulate the flow of gas, and even trigger the formation of new galaxies. These observations will help us understand the complex relationship between galaxies and the black holes at their hearts. By studying the formation and evolution of galaxies, future telescopes will not only deepen our understanding of these cosmic structures, but also shed light on the broader story of the universe. From the first flickers of light in the early universe to the majestic spirals and clusters we see today, galaxies are a testament to the dynamic and ever-changing nature of the cosmos. Next, we'll explore how space-based telescopes will revolutionize quantum communication, opening up new possibilities for exploration and discovery. Stay tuned as we continue our journey through the future of space-based technologies. Now, let's turn our attention to a groundbreaking frontier that could redefine how we communicate across the cosmos: space-based quantum communication. This cutting-edge technology promises to revolutionize not just how we explore space, but how we connect across vast interstellar distances. Imagine a future where telescopes don't just observe the universe, but also serve as the backbone of a quantum communication network, enabling instant, secure, and ultra-efficient data transfer across the solar system and beyond. At the heart of this innovation is quantum entanglement, a phenomenon where particles become linked in such a way that the state of one instantly influences the other, no matter how far apart they are. Future space-based telescopes will harness this principle to create a quantum communication network. By placing quantum-entangled particles on satellites or telescopes in orbit, we could establish a system where information is transmitted instantaneously, bypassing the limitations of traditional communication methods that rely on radio waves or lasers. This means that data from a rover on Mars or a probe in the outer solar system could reach Earth in real time without the delays caused by the vast distances involved. One of the most exciting applications of this technology is its potential to enhance deep space exploration. Imagine a scenario where astronauts on a mission to Europa or Titan can communicate with mission control on Earth without the frustrating lag that currently plagues interplanetary communication. Quantum communication would allow for seamless, real-time collaboration, making long-duration missions safer and more efficient. It could also enable the remote operation of robotic explorers with unprecedented precision, as commands and feedback would be transmitted instantaneously. But the benefits don't stop there. Quantum communication is inherently secure thanks to the principles of quantum mechanics. Any attempt to intercept or eavesdrop on a quantum signal would immediately alter its state, alerting both sender and receiver to the intrusion. This makes it an ideal solution for transmitting sensitive data, such as scientific findings or mission-critical information, without the risk of interception. In a future where space agencies and private companies are increasingly active in space, this level of security will be essential for protecting intellectual property and ensuring the success of collaborative missions. Moreover, space-based quantum communication could play a pivotal role in the search for extraterrestrial intelligence. By establishing a network of quantum-linked telescopes, we could scan the skies for signals with unparalleled sensitivity and speed. If an alien civilization were to send a quantum-encoded message, our telescopes would be uniquely equipped to detect and decode it, potentially opening the door to the first contact with an intelligent species beyond Earth. As we look to the future, the integration of quantum communication with space-based telescopes represents a leap forward in our ability to explore and understand the universe. It's a technology that bridges the gap between the microscopic world of quantum physics and the vast expanse of space, offering new possibilities for discovery and connection. Next, we'll delve into how future telescopes will measure the universe's expansion with even greater precision, refining our understanding of dark energy and the fate of the cosmos. Stay with us as we continue to explore the incredible potential of space-based technologies. Now, let's shift our gaze to one of the most profound mysteries of the cosmos, the expansion of the universe. Future space-based telescopes are set to revolutionize our understanding of this phenomenon, offering unprecedented precision in measuring how fast the universe is growing. This isn't just about numbers, it's about unlocking the secrets of dark energy, the mysterious force driving this expansion, and ultimately shaping the fate of the cosmos. At the core of this effort is the ability to observe distant celestial objects with incredible accuracy. Future telescopes will use advanced techniques like supernova surveys and baryon acoustic oscillations to track the universe's expansion over billions of years. By studying the light from these distant sources, scientists can measure how quickly galaxies are moving away from us, providing critical data to refine our understanding of dark energy. This invisible force, which makes up about 70% of the universe's energy, is the key to understanding why the expansion of the universe is accelerating rather than slowing down. One of the most exciting aspects of this research is the potential to map the universe's expansion history in unprecedented detail. Imagine a timeline that stretches from the early moments after the Big Bang to the present day, charting how the universe has grown and evolved. Future telescopes will create this map by observing millions of galaxies and supernova across vast distances. This data will allow scientists to test different theories about dark energy, such as whether it remains constant over time or changes in strength. The answers to these questions could reshape our understanding of physics itself, but the implications go even deeper. By refining our measurements of the universe's expansion, we could also gain insights into the ultimate fate of the cosmos. Will the universe continue to expand forever, eventually becoming a cold, dark void? Or could dark energy's behavior change, leading to a different outcome? These are questions that future space-based telescopes will help us answer, bringing us closer to understanding not just where we came from, but where we're headed. As we look to the future, the role of space-based telescopes in measuring universal expansion is nothing short of transformative. They will provide the data needed to solve one of the greatest puzzles in science, offering a clearer picture of the forces that shape our universe. And with each new discovery, we move one step closer to unraveling the mysteries of dark energy and the cosmos itself. This concludes our journey through 30 predictions about the future of space-based telescopes and discoveries. From ultra-high resolution imaging to quantum communication and beyond, the possibilities are as vast as the universe itself. Thank you for joining us on this exploration of the incredible technologies that will shape our understanding of the cosmos. Don't forget to like, subscribe, and hit the notification bell to stay updated on the latest breakthroughs in space exploration. The future is out there and it's waiting to be discovered. As we bring this journey to a close, let's take a moment to reflect on the incredible possibilities we've explored. From the breathtaking potential of ultra-high resolution imaging to the groundbreaking advancements in quantum communication, these 30 predictions paint a vivid picture of how space-based telescopes will revolutionize our understanding of the cosmos. Each prediction represents a step forward in our quest to unravel the mysteries of the universe, from mapping dark matter to detecting signs of extraterrestrial life. Together, they highlight the transformative power of technology and human curiosity. These advancements aren't just about scientific discovery, they're about reshaping our perspective on existence itself. By peering deeper into the cosmos than ever before, we'll uncover answers to questions that have puzzled humanity for centuries. What is the true nature of dark energy? Are we alone in the universe? How did the first stars and galaxies form? These are the kinds of questions that future space-based telescopes will help us answer, opening doors to new realms of knowledge and understanding. But the journey doesn't end here. The future of space exploration is a story still being written, and each of us has a role to play in shaping it. Whether you're a scientist, an enthusiast, or simply someone who looks up at the night sky in wonder, your curiosity fuels the progress we've discussed today. So let's keep asking questions, seeking answers, and dreaming of what lies beyond the stars. Thank you for joining us on this incredible exploration of the future of space-based telescopes and discoveries. If you found this video as exciting as we did, don't forget to like, subscribe, and hit the notification bell to stay updated on the latest breakthroughs in space exploration. The universe is vast and its secrets are waiting to be uncovered. Together, let's keep looking up and reaching for the stars. The future is out there and it's brighter than we can